So good morning all of you. So today we'll discuss different previous gate problems that are asked on basis of open system analysis, and this is lecture 2 on open system analysis. So right now, before going to the problems, I would like to recall the things that we learned in this open system analysis. So if you remember things a bit quiet, for steady state I told you rate of change of mass within the system is equal to 0 and rate of change of energy is also 0, and I told you any open system that's allowing some mass into it will also possess something called specific work which is done to maintain its own flow. And after this we have derived something called steady flow energy equation by assuming control volume and assuming different energy transactions that are happening, and finally we take this is the control volume equation, energy equation for steady state of a control volume gas flow. Correct? This is what we assumed. So good morning all of you. Yeah, so this is what steady flow energy equation that we talked about, and then we have seen different applications like nozzles, and we have seen different governing equations in nozzles, like different approximations how we have considered all these things. Then we have went for something called diffusers, and actually these are all some constitutive equations that contribute for the analysis of this open system devices. Then for turbines, compressors, and then finally we stopped at throttling. Correct? So if you recall, finally these are the things that we discussed. So now with the knowledge of all these things that we have for steady state steady flow devices, now we'll solve some problems. Okay, so let us solve some problems. Okay, so see here, this was an old gate question that came in gate in previous years. Okay, so this is the question. The first law of thermodynamics takes the form W is equal to minus delta H. Of course, the terms have their usual meaning. W indicates work interactions and H indicates enthalpy changes. So if you H denotes enthalpy of the system. So if you see the first law takes this form. If you see the steady state equation for the first law of thermodynamics. Okay, I hope this is not fine here. So let me erase the things. Okay, so see here, we know Q dot minus W dot is equal to delta KE dot plus delta PE dot plus delta H dot. This is the governing equation for the steady state flow. Correct? Now if you take this form, this Q has to be 0, this delta KE has to be 0, this delta PE has to be 0. Of course, this W dot will be equal to minus delta H dot. Of course, if you are not dealing in weights, then you can write W is equal to minus delta H. So for the equation for the first law to appear in this form, what are the cases? Now if you see a closed system undergoing a reversible adiabatic process. First of all, if a system is closed, then definitely there is no involvement of flow work in that system, which means we don't talk about enthalpies there. Correct? In general. So if you see, this is not the correct option, but if you see the second option, an open system undergoing an adiabatic process. See, for example, if this is an open system, then this equation is the energy conservation equation for this steady flow. So an open system undergoing an adiabatic process. See, if you are writing this Q dot tends to 0, which means practically there is no heat, no quantitative amount of heat that's getting transferred. So if you see, the system should be quasi-static. Next, with negligible changes in kinetic and potential energies. See here, for getting this equation from this given constitutive equation, we need to neglect this kinetic energy and potential energy terms, so that this first law, which is in this form, gets converted to W is equal to minus delta H. So this option B could make sense for us. Correct? Similarly, other two options are also closed systems, and for closed systems generally there is no involvement of flow work, so we don't have general combination of U plus PV in general. Okay. Clear to all of you why this is option B? An open system which is of course adiabatic, but both kinetic and potential energies neglected. Clear? Can I go for the next question? All of you, I want all of you to respond. See, nearly some 20 people are on live, so please respond. Did you all understand why option B is the correct option for this? Because if you want to convert this equation into this particular form, then you need to make proper assumptions such that we'll neglect some terms, and with the neglections that we considered here, this option B gets matched. So this is the next question. So Read carefully. A steam turbine receives steam steadily at 10 bar with an enthalpy of 3000 kilojoule per kg. Here, if you see, they mentioned one word, steadily, at 10 bar with an enthalpy of 3000 kilojoule per kg, and discharges at 1 bar with an enthalpy of 2700 joules per kg. I mean kilojoules per kg. The work output is 250 kilojoules per kg. Changes in kinetic and potential energies are negligible. The heat transfer from the turbine casing to the surroundings. So basically, it's given this turbine is operating under steady state, and we know turbines are generally open system devices where mass and energy interactions can also take place. So if you try to draw a turbine here, and generally, in turbines, steam expansion takes place. And let us suppose some input is here and some output is here. So now, okay, so all of you see here now. This turbine is receiving steam at 10 bar. So initial pressure P1 is equal to 10 bar. And if you write bars in kilopascals, 1 bar is equal to 100 kilopascals. So 10 bars corresponds to 1000 kilopascals. Next, with an enthalpy of 3000 kilojoules per kg. So the inlet enthalpy of the steam is 3000 kilojoule per kg. Okay. And discharges at 1 bar with enthalpy of 2700 joules. So P2 is equal to 1 bar, which is equal to 100 kPa. Next, exit enthalpy is 2700. So 2700 kilojoule per kg. Okay. The turbine work output is 250 kilojoule per kg. Means if you have a shaft connected to this turbine is giving work output at 250 kilojoules per kg. Okay. Next, the changes in kinetic and potential energies are negligible. So delta Ke and delta Pe we can assume to be 0. Then the heat transfer from the turbine casing. So generally, if you see, these turbines have some casings here to prevent any heat loss. But even though you prevent proper casing, definitely there will be some heat losses that can happen. Correct? Of course, they can be very less when compared to the actual values. But practically speaking, there will be some heat loss. So from this, some heat is lost. Okay. So what is that heat loss to the surroundings? So let us apply steady flow energy equation. We can apply steady flow energy equation because this is an open system with control volume as this. And these are the quantities that are mentioned in the question. So now you want Q dot. So let us try to solve this. We have steady flow energy equation SFW as Q minus W is equal to delta Ke plus delta Pe plus delta H. Now, they asked me in the question to neglect the kinetic energy changes and potential energy changes. Correct? And it's given the amount of work output by the turbine is 250 kilojoules per kg. See, we have some work output which is 250 kilojoule per kg, and final options are also in kilojoules per kg. So let us substitute in kilojoules per kg. So if you do that, work output is 250. So 250 is equal to, see, I am not changing any sign of this 250 because this minus W is obtained in the initial equation when we assumed that work is done by the device. Correct? So minus 250 is equal to, these two are zeros. Delta H is H2 minus H1. If you substitute in kilojoules per kg, initially the enthalpy is 3000 kilojoule per kg and this is 2700 kilojoule per kg. So if you do the calculation, delta is always final minus initial. So 2700 minus 3000. Of course, all these three quantities are in kilojoules, and the answer what we kilojoule per kg. So the answer what we get for Q is also in kilojoule per kg. So Q is equal to 2700 minus 3000. The answer is minus 300 plus 250. So this Q is equal to minus 50 kilojoule per kg. And if you see, when you compare this heat loss with respect to this enthalpy values, 2700, 3000, if you compare these two values, 50 is very small when compared to 3000. Correct? So generally, in practical cases also, turbines are very well insulated so that this heat loss from turbine to the surroundings is not, not happening that quantitatively. Okay, so this is minus 50. So here the minus sign indicates heat lost. Heat lost to the surroundings. Correct? See, in the question, okay, see, in the question it was mentioned the heat transfer from the turbine casing to the surroundings. Means definitely whenever you're evaluating Q, you should get a negative value for Q. Okay, and that's what we exactly got as 50 kilojoule per kg. Suppose if you have got positive value in the answer, definitely that's wrong, because we assume that any heat transfer out of the system is negative, and that's why we got a negative value, which is in accordance with this question. Okay, is it clear to all of you? Okay, so we are going for the next question. I hope it's clear to all of you. So this is the next question. When an ideal gas with constant specific heats, basically if they say it's constant specific heats, it's calorically perfect gas. So with constant specific heats, it's throttled adiabatically with negligible changes in kinetic and potential energies, then which of these things could happen? Actually, this S denotes entropy, which I will discuss later. Maybe another faculty may discuss that. Okay, so see here, if you see, throttling is also a steady flow. Q dot minus W dot is equal to delta KE dot plus delta PE dot plus delta H dot. So now if you see in throttling, we have seen throttling devices doesn't produce any much quantity of useful work. Next, kinetic energy changes and potential energy changes are negligible in throttling, because for small throttling devices there won't be enough time for geometrically changing the positions of the particles. So Q dot is also 0 because it's given throttled adiabatically. Correct? It's given this word adiabatically in this system. So we have delta H dot is equal to 0, which implies delta H is also 0. So if you are talking with respect to mass basis, we'll go for small letters. So delta H is equal to 0 because delta capital H is nothing but m dot into delta small h. So delta H is 0. This implies specific enthalpy change is also 0. And for ideally perfect gas, what happens? Delta H is equal to Cp delta T. So if this is equal to 0, specific heats are never 0. So delta T is equal to 0. So these are the two things that we have. Yes, option A is correct. Delta H is equal to 0 and delta T is also equal to 0. Okay, but this is also a previous gate question that was asked in one of the years. You can see in 2000 generally. For 2 marks it was asked. But if you know this particular analysis, it's really simple for us. Next, see this. A small steam vessel perfectly insulated and doing no shaft work causes a drop of 0.8 kilojoule per kg enthalpy. The kinetic energy of the steam at the entry is negligible. The velocity of the steam at the exit. Means generally, steam vessels, what they do? They generally allow some gas to escape from the given system. So if you talk about that, let us suppose we have a small vessel like this with some control volume. And let us suppose some gas is going out like this. A small steam vessel, basically steam passes through this, perfectly insulated. So this vessel is perfectly insulated, means no heat can escape out of this. Correct? This word perfectly insulated will give us the idea Q dot is equal to 0. Next, and doing no shaft work means basically this vessel is not doing any useful shaft work outside. Okay, no shaft work. This implies W dot is also is equal to 0. Causes a drop of 0.8 kilojoule per kg enthalpy. Means if you see the steam when it's passing and when it's coming out, if you see the enthalpy difference is 0.8 kilojoule per kg, and it's clearly given a drop of this much enthalpy. Means enthalpy at inlet is more than enthalpy at outlet. Neglecting, okay, the kinetic energy of the steam at entry is negligible. So initially the initial velocity when the mass is going into the system is negligible because it's given kinetic energy of the steam at entry is negligible, means initial velocity is negligible. The velocity of the steam at the exit. So if you see, if you apply steady flow equation, Q dot minus W dot is equal to delta KE dot plus delta PE dot plus delta H dot. And of course, if you see this Q dot is 0, W dot is 0, and since steam vessel is very small generally, so potentially there won't be much energy changes. So if these three are 0, then delta KE dot plus delta H dot is also 0. So if I write in terms of normal values, delta KE plus delta H is equal to 0. This equation is in weights, but this equation is generally in terms of whole magnitudes of work. So delta KE, final minus initial, because this delta sign always denotes final minus initial, m dot by 2 into V out square minus V in square plus m dot into H out minus H. Okay. H out minus, I think something happened. Okay, so see here. H out minus H in. Okay. Is equal to 0. So if you see this m dot, I am cancelling this because it's same for the device to operate under steady cases. This V in is also 0 because it's given the kinetic energy of the steam at the end is negligible, which means the inlet velocity is very small. So this implies V out square by 2 is equal to H out minus H in with a minus sign, because here both the terms are on same side of the equation, but now we are bringing out. So this implies V out is equal to 2 into H in minus H out. Of course, there is square here. So this is the equation that we have. V out square is equal to 2 times of H in minus H out. So if you work out this, V out is equal to square root of 2 into H in minus H out. But if you see, this velocity V is given in meters per second, correct? So if you see here, okay, this velocity V options are given in meters per second, but here H is given in kilojoules per kg. So for doing that, V out is equal to square root of 2 into, it's given the enthalpy drop is 0.8 kilojoules. 0.8 kilojoules correspond to 800 joules per kg. So if you calculate this value, V out is equal to square root of 1600 is 40 meters per second. So this is the exit velocity of steam from the steam vessel. Okay. Clear to all of you? Can I go for the next question? I hope there is no issue with this question. It's a simple study flow application. You can, So take this question. Some common data for next two questions. Okay, the inlet and outlet conditions of the steam for an adiabatic steam turbine are as follows. See, it's given the turbine is adiabatic. If the turbine is adiabatic, there is some insulation on this. Correct? It doesn't allow any heat to go out. Adiabatic turbine means no heat interactions are allowed. Okay. Next. Of course, these are the values, inlet and outlet conditions. So see what he's asking for. If mass flow rate of the steam through the turbine is some 20 kg per second, the power output of the turbine. So see here. Let me. Okay, I think it's not willing to come. Let us keep it there. So see here. Solution. For this, look, the power output of the turbine in megawatts. So let us see. If you apply the steady flow energy equation again, Q dot minus W dot is equal to delta Ke dot plus delta Pe dot plus delta H dot. Okay, so now given the turbine is adiabatic, it's already given in the question. So kinetic energy values and potential energy values we need to consider, because they have given some changes in elevation. Z2 has 6 meters, Z1 has 10 meters and all these things. So we'll consider all this, and pressure values are also given. Of course, you know, in a turbine pressure actually drops. So if you see, considering all these values, W dot is equal to minus delta Ke dot plus delta Pe dot plus delta H dot. So this implies W dot is equal to minus of this total change in kinetic energy is nothing but mass flow rate into specific kinetic energy. Similarly, total potential energy is nothing but mass flow rate into potential change in specific potential energy, and similarly specific enthalpy. So m dot into delta K is small. So delta K is small will be equal to V out square minus V in square divided by 2 plus G into Z out minus Z in plus H2 minus H1 means H out minus H in. But here one thing you need to be careful is this H out minus H in should be in joules per kg, because the total all these values are in joules per second. So this should be also in joules per second. It's not kg. This is also okay. Since we are multiplying with mass, this is joule per kg and kg per second. Okay. So now if you see W dot is equal to, see what happens. W dot is equal to minus m dot. M dot is given 20 kgs per second. Yes or no? It's already mentioned. So minus 20 into V out square minus V in square. Let us go for the data. If you see, this V2 is 100 meters per second and this V1 is 160 meters per second. So V out square minus V in square is 100 square minus 160 square. So this is 100 square minus 160 square divided by 2 plus G value. Did they ask us to for any value of Z? Okay. So we'll take 9.81 into Z out minus Z in. If you see, outlet is at an elevation of 6 meters and inlet is at an elevation of 10 meters. So 6 minus 10 plus H out minus H in. So if you see, H out is 2600 kilojoule per kg and this is 3200. So net difference is 600. H out minus H in is minus 6. Minus 600. So if you see, H out minus H in is minus 600 into 10 cube, because this should be in joule per kg and the given options are in kilojoule per kg. So now let us evaluate this value. So W dot is equal to minus 20 into, see here, 100 square minus 160 square. This can be written as minus 60 into 260 divided by 2 plus 9.81 into minus 4. Generally, you know, these values are very small, plus minus 600 into 10 cube. So this is the value that we need to calculate. 10 power minus 3. Why? This is in kilojoules per kg, and to convert kilojoules per kg into joules per kg, we need to multiply into 10 cube. Okay? So please evaluate this value. See, actually in a turbine, this potential energy changes and kinetic energy changes are very small. But if you see, two options are very close, 12.157 and 12.941. And of course, these two options are also very close. So if you neglect some terms, there might be a chance that your answer gets diverted from the actual answer. So if you calculate this value, this is 130 times. So shall we calculate this value? Let us calculate by taking help of a calculator. So see here, let us calculate this values now. Minus 60 into 130, correct? Minus 60 into 130. Okay, let us cancel this minus sign totally here in all three places. So we'll be getting positive values. Okay. Okay, see here. So we'll cancel all these minus signs with a plus sign here. So now let us calculate this value, 12.156 megawatts. Okay, 12.157 is in the answer, Muniswami. So I hope you are correct. So let us calculate this value, 60 into 130 plus 9.81 into 4 plus 60,000. Okay, 600,000. Let us do that. 60 into 1. Okay. 60 into 130 plus 9.81 into 4 plus 600 into 10 cube. So 1, 2, 3 digits. Okay. Is equal to this into mass flow. It is given as 20 kilojoule per second. So 121.567. Of course, all these values are in joules per second. So if you want in megawatts, 6 digits from here. So if you put a decimal here, 12.156 could be the correct answer for this. So 12.156, which is 12.157, which is already given here. Okay. $12.157 is the correct answer. But you should be very careful with these numbers, otherwise your answers change. Okay. So A is the correct answer for this. Clear to all of you? Can I move ahead? Did you all get 12.157? Please check the values. Okay. Remaining people, did you get? See, already 9 people I think online. So tell me, aren't you getting this 12.157 megawatts? Got it? Okay. If you get it, then we'll move for the next question. Assume the above turbine to be a part of a simple Rankine cycle. Okay, we'll see what is a Rankine cycle and all at later stages. The density of water at the inlet to the pump is 1000 kilojoule per, kg per meter cube. Ignoring kinetic and potential effects, the specific work supplied to the pump. So basically, they're asking you what's the specific work that is supplied to the pump. So see here, pressure difference is given here. See, pressure difference is given. P inlet is equal to 3 MPa, which is 3000 kPa, and P outlet is equal to 70 kPa. And you know, specific water, generally fluids are incompressible. So specific water, density actually is equal to 10 cube per kg per meter cube. So, you know, for any steady flow device, work input is equal to minus integral VdP. Please consider this. I'll show you this formula, how it's coming after we talk something called TDS equations in entropy. Okay. But generally, if any device like pumps and all, work input is minus integral of VdP. This is called, steady flow work, which we see in later stages, because I need to show you TDS equations to show how this expression is coming. Okay. So we'll be getting this in general, minus integral VdP. So here the advantage is given, it's a fluid. So this V is a constant, because practically fluids are not compressible or incompressible. So the specific volume doesn't changes along the pressure change. Correct? Generally, if you compress water, bulk modulus of water is so huge that you need to apply tremendous amount of pressure to compress its volume by a very small amount. So if you see, this V can be assumed as a constant, and V is nothing but 1 by rho. So if V is a constant, then integral dP is nothing but change in pressure. So this is equal to minus V into P2 minus P1. Okay, since we are calling it as work input, 10 power minus 3 into P2 minus P1. P2 is 70 kPa minus 70 kPa minus 3000 kPa. So the answer is minus 10 cube into minus 2930. So minus minus gets cancelled. So 2.90 kilowatts. Watts? No, it's work input, right? And we are multiplying with B. So this is kilojoule per kg. 2.93 is the answer. So this is the formula for work input of any steady flow device. For the time being, please remember this. I'll show you how this is coming in TDS equations, after TDS equations. Okay. So 2.93 is the answer. So if you see, 2.93, option C is here. Okay. So W input is equal to minus integral VdP, where pressure is changing from P1 to P2. Here V is constant. V is constant since fluids are practically incompressible. Fluid in the sense like liquids, you can write. Since water, you can write water is incompressible. So therefore, W input is equal to, since we are writing specific volume, answers will be in kilojoule per kg minus V into integral P into P out dP. So this is equal to minus V into P out minus P in. Since we are writing the word input, we can always, yes, but I'm writing here input, so you can eliminate the minus sign there. Okay. For this calculation I have given in the first slide. So V is 10 power minus 3 because you know specific volume is nothing but 1 by density. Correct? Because specific volume means mass by volume, but here density means, density means mass by volume, but specific volume means volume by unit mass. So these are the cases. Or else if you want, you can write work input is equal to minus, okay, you can write P in minus P out. If you eliminate that minus sign, divided by density. All these are formulas for work input. Okay. See, since we are mentioning the term input here, you can eliminate this minus sign here. So I'm going for the next question. See this. A convergent divergent nozzle. Okay. The temperature and pressure of A in a large reservoir are 400 Kelvin and 3 kPa. Okay, 3 bar. So it means if you see, if this is the large reservoir, here the pressure is 3 bar. So P is equal to 3 bar, which is equal to 300 kPa. And what about temperature? Temperature is equal to 400 Kelvin. Okay. And this is a reservoir which is having gas at these conditions. A converging diverging nozzle of exit area 0.005. So this area A is equal to 0.005 meter square, of course. Then is fitted to the wall of the reservoir. The static pressure of A at the exit section means here. Here the static pressure P is equal to, how much is the static pressure here? The static pressure of A at the exit section for the isentropic flow through the nozzle is 50 kPa. So here this P exit is 50 kPa. Next, the characteristic gas constant is 0.287 kilojoule per kg and the ratio of specific heats, basically K, Cp by Cv value is 1.4. That's what it's given in the question. So there is one converging diverging nozzle. Generally, you know, rockets use this because generally we have an intuition. Let me tell you small thing about this. Generally we have an intuition that if cross section decreases, velocity increases. Correct? But it's not true in all the cases. This condition is valid only for subsonic flows, means flows which are taking below the sonic velocity. This condition is valid, means basically dV by dA means rate of change of velocity with respect to area is negative if Mach number is less than 1. Of course we don't deal this in this course, but I'm telling you there's something called compressible fluid flow. So there means basically when fluid is capable of getting compressed during its own flow, this is less than 0 if Mach number is less than 1. What is a Mach number? Generally this Mach number means actual velocity by acoustic velocity, means sound velocity in a given condition. So these are the cases, but dV by dA is greater than 0 if Mach is greater than 1. Okay. So generally when fluids are moving like rockets, space shuttles, all this, if they are moving at speeds more than acoustic velocity in that medium, dV by dA is 0. Means actually whenever at the nozzle inlet at the initial conditions velocity is 0, practically till Mach 1 you need converging nozzle. Okay, because fluid gets accelerated. Because for the positive change in dV means for the velocity to increase, area should decrease. That's what you have here. Once the fluid attained the max speed, then they want to further increase the speed. For that, you should have dV by dA greater than 0. For the velocity to further increase, the area should also increase. So therefore, they'll diverge. And this kind of nozzles they generally use in vehicles which move at more than max speed. Means like supersonic vehicles and all. They take advantage of this. Okay, so that's why practically we use converging diverging nozzles because of this relation. But anyhow, this relation is not a part of this course, so we'll deal that in compressible gas mechanics. So these are the conditions. So whatever they want. So this is data given for us. Some inlet conditions and exit conditions are given. So let us see what they want. The density of A in kg per meter cube at the nozzle exit. Okay, so they want the density of A here. Okay, density of A at the exit. So see here, let us write data once. Given T inlet is equal to 400 Kelvin, next, and 3 bar respectively. So P in is equal to 3 bar, which is equal to 300 kPa. Next, what did they mention? A converging diverging nozzle. Okay, area at the exit is 0.005 meter square. So A exit is equal to area at exit is equal to 0.005 meter square. Okay. Next, is fitted to the wall of the nozzle as shown in the figure. The static pressure of A at the exit section for the isentropic flow to the nozzle is 50 kPa. Okay, so see here. P exit, of course we are dealing with only static pressures, is 50 kPa. And isentropic flows, we didn't discuss entropy, but isentropic flow is the flow which is actually reversibly adiabatic. Means if there is a reversible adiabatic process, later in the later stage of the course, we see there is some property called entropy. That particular property, like how internal energy is there for closed systems, entropy is also associated with any of the systems that we deal with. And this for reversible adiabatic flows, this entropy remains constant, which we see later in later stages. Okay, so Q dot is equal to 0. That's what we mean by this isentropic word. Okay, the characteristic gas constant is 0.287. So R is equal to 0.287 kilojoule per kg, and K, which is basically the ratio of Cp by Cv, it's given as 1.4. See, you can ask me one thing here. They have mentioned the ratio of specific heats, but they didn't mention Cp by Cv or Cv by Cp. But I already shown you Cp is always greater than Cv for compressible fluids. So if you see, this is 1.4. Now, what they are asking for, the density of A in kg per meter cube at the nozzle exit. See, if A is treated as an ideal gas, then definitely the flow is adiabatic reversible. Correct? For reversible adiabatic flows, we have temperature versus pressure relationship. Correct? We have P in 1 power gamma is equal to, or 1 minus K into T inlet power K is equal to P out power 1 minus K into T, all since pressures are given. Okay, but we don't have a volume. Let us find the temperature first, so we can calculate T out whole power K. So what is the expression for T out? T out is equal to P in divided by P out whole power 1 minus K divided by K into T in. So this is the value. Now we have the value of P inlet, P outlet, K value and T in value. See, all four parameters are present. T in is present, P inlet is present, P exit is present, and also K value 1.4 is also present. So we can write T out. Once you get T out, you can write, we can apply ideal gas equation. PV is equal to RT. So R, T and P. So you can get this density. So please try to find. Video is buffering to all of you. For how many of you video is buffering? Not buffering? Okay, so I hope now there is some issue with your net connection. So please calculate and tell me the value of T out. Okay, so please calculate and tell me the value of T out. What could be the value of T out? Okay, not buffering. So please now look at your connection once. So tell me what could be the value of this. You have all the values here, P in, P out. Then K value is given, T in is also given, 400 Kelvin. So please tell me what could be the answer. Please solve, use your calculator and calculate this value. 240 around. Okay, so now once you get T out, let us apply ideal gas equation at exit. So because they want at the nozzle exit, so P exit into V exit is equal to, okay, this V corresponds to specific volume, V exit is equal to R into T exit. and you are getting T exit value here, T out. Okay, 239.73. Fine. So if you get this T out as 239.73, I'm trusting you, so I'm putting it 239.73 Kelvin. Now see here, you can calculate specific volume out of this. PV is equal to RT. So P at exit is given as 50 kPa static pressure into volume of exit. This is what you need to find. R into R value is 0.287. Since we substituted 50 in kilopascals, this 0.287 should be in kilojoules. So 239.73, we are putting it here. So if you want 1 by V exit, means density exit is equal to 50 divided by 0.287 into 239.73. This is the value in kg per second. So please calculate this value. You will be getting density of this gas at the exit. Please calculate this value. Punch your calculator and tell me this value. Density 0.72. Okay, 0.727. See, this is a very simple question. Just applying, this Q is equal to 0. Yeah, 0.7267 means 0.2727, which is close to the option that is given here, 0.727. So I agree, that's 0.727 is the correct answer. So if you see this, just read the data, then you have enough data to work out the things. So now if you apply, because of this reversible adiabaticness, since we have the pressure temperature relation for adiabatic process in this way, we can substitute the values. Out of these 4 quantities, out of these 5 quantities, 4 quantities are given. So if you calculate the 5th quantity, then applying the ideal gas equation, density at exit is equal to 50 by 0.287 into 239.73. So if you calculate this value, you will be getting 0.727. Okay, but you should be very careful in calculating these values. I hope some of you didn't get this because of the calculations problem, correct? Is there someone who didn't get these calculations? You're okay with the expressions, but these values are giving you trouble? Is there someone with such case? You understood this everything, but this calculation is not fine. If there is someone, I'll let you know. We have a calculator in the background. We'll work out the things. If that's fine, we'll go for the next question. So 0.727 is the density of the gas at the exit. Okay. So I'm moving ahead. Can I move ahead now? Clear? Okay. So finally we got density at exit is equal to 0.727 kg per meter cube. Okay. This is where we ended up. Now the mass flow rate to the nozzle. Mass flow rate is given by density into area into velocity at that particular cross section. So if you talk about exit, O exit, since we have exit into A exit, which is also given into V exit. Means this V exit is the quantity you need to find, means the exit velocity is the quantity that you need to find, in order to calculate these things. And for a nozzle, the constitutive equation for adiabatic nozzle is delta Ke plus delta H is equal to 0. And delta H for ideal gas is Cp into temperature differences. So, and initially the velocity from the reservoir is very less compared to the exit velocity of the nozzle. So if you make all such assumptions, we'll be getting V exit square by 2 plus Cp into T exit minus T inlet is equal to 0. And R and K values are given, so you can calculate Cp, because Cp is equal to K into R by K minus 1. We gave this expression. Cp is equal to this expression we have already mentioned. So K is given, R is given, you can calculate the values, where K is Cp by Cv. So V exit is equal to square root of 2 Cp into T inlet minus T exit. This formula we have already given, but the caution I gave you is to get this in meters per second, you need to substitute this Cp in joule per kg. Okay, so if you calculate these values, this expression I have already given you. So V exit is equal to square root of 2 into Cp is 1005 is what you get when you substitute 0.287 and 1.4 there, and T inlet minus T exit. T inlet is 400 Kelvin minus T exit, you just told 239.7 something, 239.73. Okay, so 239.73. If you can perform this calculation, you will be getting this V exit value in meters per second. So please calculate and tell me this value, meters per second value. So if you get this V exit, you can substitute here. A exit is given, O exit you already found out. You can find out what is the mass flow rate. See, just 2-3 steps, simple steps, but the whole thing lies in understanding the constitutive equations. So please tell me, for this nozzle, what should be the conditions of velocity? What's the velocity value at exit condition? You can write for adiabatic nozzle, since it's already mentioned in the question. And I told you why generally nozzles are also adiabatic practically, with very minute heat interactions from the surroundings. $567.43. Okay, considerably a reasonable value. 43. I guess you are correct, Deepak, because generally nozzle velocities are such range because there is a converging diverging nozzle, so velocity should be greater than sound speed. So values could be more than 330. So 567 could be one of the options. D 2.06 is the mass flow rate. Okay, first tell me this V exit value 567.436. If this is the case, then m dot is equal to rho exit into A exit into V exit. So rho exit you found 0.727. A exit it's given in the question 0.005, and velocity some of our friends are telling 567.436 meters per second. Generally nozzles, nozzles are fitted to devices, and devices generally vehicles move at this speed. So 567.436. So what could be the value? 2.06 kg per second. That's what one of us is telling. So m dot mass flow rate is 2.06 kg per second. D. Okay, Deepak, I hope both of you are correct, getting same answers, reasonably comparatively good. So 2.06 kg per second is the mass flow rate that is associated for this given nozzle. Okay. So am I clear to all of you for this question? Did you all understand this? See, this equation I already gave you for nozzles, because if you apply steady flow energy equation, nozzles are practically adiabatic. So this Q term in this steady flow energy equation will go for 0. Similarly, potential energy changes will be negligible. So that is also 0. And nozzles alone, they don't produce any work output. So W dot is also 0. So then the terms that is left with steady flow energy equation is change in kinetic energy plus change in enthalpy should be equal to 0 basically. Okay. Fine. So I'm moving for the next question. So this is the next question. Common data for next two questions. Okay. Because in generally in recent years of GATE, this kind of questions are being asked. So if you see, this question is in 2011 and this question is in 2012, things like this. Okay. So read this question. Common data for next two questions. A enters an adiabatic nozzle at 300 kilopascals and 500 Kelvin with a velocity of 10 meters per second. But in this case, some initial velocity which is to be considered is also given, and that initial velocity is 10 meters per second. If you see, the exit velocity is 180 meters per second. So if you compare the values, generally nozzles highly accelerate the fluid. So inlet velocities will be many times less than the outlet velocity. The inlet area is 80 centimeters square. The specific heat of air Cp is 1008 joule per kg Kelvin. Okay. Then if this is the data, what is the exit temperature of the air? Okay. So let me draw one nozzle here first. Nozzles generally they accelerate the fluid. So if this is the control volume that is available to us, so this is the control volume. Now let us talk about the things. Air enters at 300 kilopascals and 500 Kelvin. So P in is equal to 300 kilopascals and T in is equal to 500 Kelvin. Okay. Generally, combustion gases go into this. So generally, these inlet temperatures are very high for A. Okay. Next, the initial velocity is 10 meters per second. The initial velocity is 10 meters per second. It leaves the nozzle at 100 kPa with velocity of 180 meters per second. So if you see, this V in is given as 10 meters per second, and this V exit is given as 180 meters per second, which is comparatively huge. And P exit, what about P exit? It's given 100 kilopascals. Okay, so P exit is equal to 100 kilopascals. So if this is the case, then what he's asking for, the exit temperature of the air. So T exit. Okay. So if you apply steady flow energy equation as usual, so for adiabatic nozzle, see, it's clearly mentioned the nozzle is adiabatic. So if the nozzle is adiabatic, we have some insulation. Since Cp is also given, let us apply the steady flow energy equation. So 484 I hope it could be correct because temperature will be very less. Less when compared to this 500. So SFW, if you apply the steady flow energy equation, Q minus W is equal to delta KE plus delta PE plus delta H. Let us write this E capital here. Okay, so now given its adiabatic nozzle 516, Nagasai, tell me one thing. Whenever you are passing your fluid through a nozzle, will the temperature reduce or it increases? Understood, Nagasai? See, generally, nozzle increases the kinetic energy of the fluid at the expense of enthalpy of the fluid. Correct? If enthalpy is decreasing and if kinetic energy is increasing, if enthalpy is decreasing, will the temperature of an ideal gas decrease or increase in general? It should decrease, correct? Because enthalpy of an ideal gas is directly proportional to its temperature. So if enthalpy is decreasing, temperature should decrease definitely. And 516 is more than 500. Okay, I am using that formula. See here. And nozzles, they do not produce any work. Potential energies, nothing is mentioned about datums. So this is also 0. So this implies delta KE plus delta H. So m dot into V out square minus V in square divided by 2 plus m dot into Cp into T out minus T in. This quantity has to be 0. And since operating under steady cases, both m dots, if I cancel, V in, some information is given, V out information is given, Cp information is given, T out, we need to find out, T in information is given to us. So let us calculate the things. So V square out minus V in square is equal to 2 times Cp into C. If you shift this equation to the right hand side, one minus sign comes here. To eliminate that minus sign, I am writing T inlet minus T outlet. So this is the constitutive equation to find out the relation between velocities. Correct? Temperatures are also given. So if you see, this implies V out square minus V in square divided by 2 into Cp is equal to, so if you see here clearly, V out square minus V in square divided by 2 Cp is equal to T in minus T out. So what could be T out from this? T in minus V out square minus V in square divided by 2 into Cp. So I am applying this equation, Nagasai, what you told. So see here, T out is equal to T in. What is T in? 500 Kelvin minus V out. It's given velocity at outlet is 180 square. So 180 square minus 10 square divided by 2 into, I told you need to substitute this Cp in joules per kg. So this is 1008. So if you perform this calculation, this value could be something like T out is equal to 500 minus, see, this is of the form a square minus b square format. So 190 into 170 divided by 2 into 1008. Some of you please perform this calculation and tell me the answer in Kelvin. 484. Okay, now I hope you got the things. 484 is the answer. So if you see, this option is in C, correct? So 484 Kelvin. See, Nagsai, if you see here, some of you might perform this calculation in a wrong way by forgetting this minus sign here. If you forget this minus sign, this 16 which is to be subtracted from 500 will be added to the 500 and you'll get 516, which you got now. Okay, and that's why it's given as first option. But the practical thing in nozzles is, nozzles increase the kinetic energy of the fluid at the expense of enthalpy, correct? Means to increase the kinetic energy of the fluid, they use the enthalpy that is stored within the fluid. So if the kinetic energy is increasing, definitely since total energy has to remain constant, so when kinetic energy is increasing, enthalpy should decrease. And if enthalpy is decreasing, since we are assuming ideal gas assumption, enthalpy is directly proportional to temperature. So if enthalpy is decreasing, temperature should decrease, which means first two options are straight away wrong. In exam, if you don't have time, but if you have some minimum idea about nozzles, now guessing out of 4 options is very dangerous. So you know answer won't be more than 500. So you'll eliminate option A and option B straight away. Then out of these two, you can go for some calculation again. Okay, clear to all of you? So we'll move for the next question. The exit area of the nozzle in centimeter square. You know, nozzles, they satisfy the continuity equation. Any device in which mass is flowing should satisfy the continuity equation. So A1 V1 by specific volume, actually O1 A1 V1, the density which is in the numerator, I am writing it as specific volume in the denominator, so things doesn't change much. A2 V2 divided by V2. Now see, we know information about, did they give some information about specific volumes or something? No, but they have given information about pressures. Okay, so we can deal the case. So see here, in is equal to, instead of 2's we can write exits. That could look nice. So A exit, V exit divided by V exit, correct? Instead of the specific volume, since we have ideal gas equation as PV is equal to RT, instead of V we'll write P by RT. If you write this, A inlet into V inlet divided by, in case of the specific volume we'll go for P inlet divided by, okay, this is R into T inlet divided by P inlet is equal to A exit into V exit divided by R into T exit into, divided by P exit. So if you see, this R is a constant in both sides of the equation. So if you want to write an expression for A exit, this implies A exit is equal to A in into V in divided by V exit. So V at inlet divided by V at exit into T at exit divided by T at inlet, T at exit divided by T at inlet into, if you see again, P inlet divided by P exit. So this is the formulation that you have for calculating exit area. So here options are given in centimeter square because this term in centimeter square is mentioned here. So if you go back, the initial area is also given in 80 centimeter square. If you see, the inlet area is 80 centimeter square. So let us not disturb the units anyway. So if you write this expression again, A exit is equal to A at inlet into V inlet by V exit, V in divided by V exit into T exit divided by T inlet into P inlet divided by P exit. So now you have all the values. See here, A exit is equal to, see, A inlet value, it's given in the data 80 centimeter square. So 80 into 12.96. Vamsi, I hope that could be reasonably correct, because generally, you know, V inlet is given 10 and V exit is 180 meters per second. Both are in meters per second, so no issues. T at exit, we got 484 divided by T at inlet, which is 500, into P at inlet. At inlet conditions, pressure is given 300 kilopascals. So 300 kilopascals divided by, generally there exists some, you know, this pressure drop. So this exit pressure is given 100 kilopascals. So if you see, this is 100. So now you can calculate the values. This 0 gets cancelled. This 100 cancels this 300 3 times, and you can cancel one more 0 if you want. Then 3 gets cancelled 6 times. Calculations you can perform. I am leaving it for you. 8 into 484 divided by 6 into 50. You can go for 2 table and all, but I think you can calculate the values. Calculate this value. 50, suppose if I take it 500, around 10 times, 80 by 6, 12 point something could be the answer actually. Yeah, 12.9 could be reasonably correct. 12.9, this is area, so centimeter square. 12.9. Because even if you perform some rough analysis, since options are far away, 56, 12, 4, 90 and all. So if you take this as 500, 50 by 500 is 10. So 10 8s are 80, 80 by 6 will be 12.5 around. Okay. So 12.9 is the only option which is close to that. You can go for that. Okay, so for this you need not use any calculator. But see, the way we are writing the equations tells us everything. Okay, if you are writing equations in a good way, suppose if your answer doesn't match with options, you can check clearly which options, which things are not matching here. Okay, so you can spend enough time on that in examination. So can we move for next question? Are you all okay with this 12.9 centimeter square? Okay, so we are going ahead for the next question. I hope things are very much easy, correct? I am not using any rocket science here, but simple steady flow energy equation analysis. Actually, my chat box got disconnected, so I am looking for the comments. Okay. Net signal is not certain, so I need to move here and there. Okay, so this is the next question. For an ideal gas with constant values of specific heats, for calculation of specific enthalpy, generally enthalpy of any gas is function of temperature and pressure, but for ideal gases, in chapter thermodynamic relations, we will show you that specific heats of ideal gas is just based on temperature, but for the time being, this is for any gas in general. For ideal gas, H is a function of temperature alone. Okay, this will solve in the thermodynamic relations chapter. Will show you why internal energies and enthalpies of ideal gas depend only on temperatures. Okay, so please at this moment please try to take a note of this. For ideal gas, this specific heats calculation, once if Cp and Cv are fixed, they depend only on temperature. Okay. So I'm going for the next question because there is nothing big to deal with this particular question. So this is the next question. So if you see, work is done on an adiabatic system due to which its velocity changes from 10 meters per second to 20 meters per second. Elevation increases by 20 meters and temperature increases by 1 Kelvin. The mass of the system is 10 kg. So some data is given regarding one system and acceleration due to gravity, gravitational acceleration. It's given 10 meters per second square. If there is no change in any other component of the energy of the system, the magnitude of the total work done. So let us write steady flow energy equation for this, because you can see there is some velocity change at inlet and outlet. Of course, if there is some velocity at inlet and outlet, that means some mass is capable of coming in and some mass is capable of going out. So let us suppose there is an adiabatic system. By the moment I say adiabatic system, no heat transactions can occur between the system and the surroundings. Okay, yes, this is the case. So if this is surroundings, okay, so this is surroundings. So now it is given the system is adiabatic. If this is adiabatic, heat interaction is 0, not allowed. Okay, work is done on the system, so there is some work input to the system. Okay, velocity changes. V1 V inlet is 10 meters per second, and let us suppose V outlet is somewhere here. So V outlet is 20 meters per second. Okay. Next, elevation increases by 20 centimeters. Means if this is Z inlet, then Z outlet is equal to Z inlet plus, it was told the elevation increased by 20 meters. So this is plus 20 meters, of course. Next, and the temperature increases by 1 Kelvin. So if this is temperature T in, this T exit or T out is equal to T in plus 1. Okay. Next, mass of the system is 10 kg. Okay. M is equal to 10 kg. Fine. Mass is also given for this system. Next, CV is 100 joule per kg Kelvin. Okay. CV value is 100 joule per kg Kelvin. And acceleration due to gravity, Z is equal to 10 meters per second square. See, here they have asked us to assume it as 10, but if they didn't ask us, we are not supposed to take 10. We should take only 9.81 here. Okay, at this instant. So if you see this, Z is equal to 10 meters per second square. If there is no change in any other component of the energy of the system, the magnitude of the total work done. So let us apply steady flow energy equation. SFW. Q minus W is equal to delta KE plus delta PE plus delta H. Okay, so see here. See, the temperature increased by 1 Kelvin, that's what we have. So see here. Q is 0 because it's given the device is insulated. So minus W is equal to, see this minus W, we assume that the work is done by the system, but it's clearly given work is done on an adiabatic system. Means if work is done on the system, you can straight away write this minus W as work input. Okay, so work input is equal to delta KE M dot into V out square minus V in square divided by 2. Okay, we'll remove this dot because we are dealing in total quantities, plus M into G into Z out minus Z in plus this delta H can be written as M into Cp into T2 minus T1 or T out minus T in. Okay, so this implies W input is equal to M, mass of the system is given 10 kg. Okay, so this is 10 kg into V out square, 20 is the exit velocity given and inlet velocity is 10. So if you see 20 square minus 10 square divided by 2 plus mg, mass is 10, gravity is again assumed to be 10. So Z out minus Z in. If you see Z out is Z in plus 20, so Z out minus Z in is 20. Plus, see, now this term enthalpy is a combination of internal energy plus flow work, but it's clearly given in the question. There is no change in any other component of the energy, means only the temperature is raised. But generally, if you see, enthalpy is a combination of internal energy plus flow work. But apart from these work transactions, it's clearly mentioned there is no change in any other component of the energy, means basically the changes with respect to flow energies is 0. So instead of this writing Cp here, we can go for Cv, because we are writing Cv in place of Cp because change in flow work is negligible. Is 0 because it's mentioned there is no change in any other component of the energies. So if this is the case, M is again 10, Cv. Since all these are in meters per second and in meters, Cv we will put in joules. So this is 100 into T out minus T in. It's given temperature of the system increased by 1 Kelvin. So this is 1. So did you all understand why we have replaced this delta H with Cv? Because delta H is same as delta U in this case, because flow work is not changing. Because in the question it's clearly mentioned there is no change in any other component of the energy. So this is the value that input we are putting. This minus W, we consider this as work input. By the time you are telling already input, you need not put a minus sign again. So W input is equal to 10 into 20 square minus 10 square, which is 200. 400 minus 100, which is 300. 300 divided by 2 is 150. Plus 2000 plus one more 1000. So if you see 2 plus 15, 35. 35 plus 10, 45. So this is 4.5 kilojoules is the work input that you are adding to the system to cause all these changes. So this implies work input is equal to 4.5 kilojoules. See, in exam, you should look carefully whether they are asking for the magnitude or the actual value. Because if there comes a minus sign and if they are asking for the magnitude, you should put that value itself. You shouldn't consider the sign. Okay, but of course, this is a different case. In exam, you should be very careful in looking at the questions. See, if you see here, see, in the question it was asked the magnitude of the total work. Suppose if you enter with a negative sign, the answer changes because negative numbers and positive numbers are two different sets. So numerical doesn't get matched, and you will be awarded wrong marks even after performing all these calculations. Okay, so please look the question carefully. The magnitude was asked in the question. It was a GATE 2015 question. If you see it, for 2 marks it was asked. So 4.5 kilojoules. The total work done in kilojoules is 4.5. Okay, and also you should check for the values. Yes, Deepak, it's correct. In kilojoules, you should check for the units and for the magnitude or for the sign changes. Okay, so please be careful with that. Next, so did you all understand this question? Why it's 4.5? Most importantly, you should understand why did I equate these two. Delta H is same as delta U, because in the question it was mentioned no other component of energy is changed. So flow work, whatever energy is coming in terms of flow work, that is going out as flow work. Yeah, if they ask work input, definitely we should write positive value 1C, no issues. Okay, so we'll go for next question. Steam enters a turbine at 30 bar and 300 degrees centigrade. U is 2750 and H is 2993. See, 2993 kilojoules for 1 kg of steam. See what is huge enthalpy it's having. And exits the turbine as saturated liquid. We'll see what is a saturated liquid, but our main interest at this point of time is U and H values. Okay. Heat lost to the surroundings is 50 kilojoule per kg of steam flowing through the turbine. Neglecting changes in kinetic and potential energies, work output of the turbine in kilojoules per kg of steam. Okay, so now let us see. There is one turbine. Okay, so steam is entering this turbine at 30 bar. So P at inlet is equal to 30 bar, and you know this 30 bar, 1 bar is equal to 100 kilopascals. So 30 bar corresponds to 3000 kilopascals. Okay, next, temperature T is equal to 573 Kelvin, because this is 300. See, practically waiting, you should write 573.15, but since 0.15 is very small when compared to 573, I am neglecting that 0.15. Okay, but practically we have seen in thermodynamic scales, if you see temperature in degrees centigrade should be converted into Kelvin, then for the value in degrees centigrade you will add 273.15. Correct? We have seen that in 0th law of thermodynamics when we are discussing temperature scales. So 573.15 is the actual answer, but since this 0.15 is very small when compared to the figures that are present here, I am neglecting that. Okay, so U is equal to, this is at inlet condition of course, U at inlet is 2750 kilojoule per kg, and H at inlet is also equal to 226 kilojoule per kg. Okay, next, heat loss to the surroundings is 50 kilojoule per kg. So definitely there is some heat loss from the turbine. Whatever might be your insulation levels, definitely some energy gets lost in form of heat. So Q out is equal to 50 kilojoule per kg. Okay, next. Yeah, that's it. Neglecting the changes in kinetic and potential energies, work output from the turbine. Exit values are also given. For the exit, see, for the exit U is equal to 225 kilojoule per kg and H is equal to 226 kilojoule per kg. One thing, if you see here, when fluid is saturated liquid, like when it's normally the liquid at its boiling point, the U and H values are very close, because the specific volumes are generally very low when compared to this particular situations. Like 30 bar and 300 degrees centigrade is very high pressure, and 30 bar is such a huge tremendous pressure, and 300 degrees centigrade at this particular combination, specific volume will be very high, okay, for the steam. But when it comes to the bottom, the pressure at which these turbines leave the exit of the, at where the turbine exit is located, there the pressure is generally very low. For example, in power plants, in Rankine cycles and all, if you see, the pressure of the condenser where the heat is getting ejected or where the turbine is giving its exit will be very less when compared to the atmospheric pressure, like 30 kilopascals, 40 kilopascals hardly. Okay, so since H is equal to U plus PV, and since this P and V both are very low at this condition, this U and H will be almost same. Okay, so these are some observations that you could make while viewing the rings. So anyhow, at this particular moment, that's not the main point of interest. So if you see here, if you apply steady flow energy equation, Q minus W is equal to delta KE plus delta PE plus delta H. So if this is the case, see, heat loss to the surroundings, heat loss is taken as negative. So minus 50 minus W is equal to, okay, this is in kilojoules. Neglecting changes in kinetic and potential energies. So these two are neglected. Okay. Delta H. Now what is delta H? This delta H is H outlet minus H inlet. And if you see, H outlet is minus 226. So 226 minus H inlet. H inlet is 2993. So if you see the values, work output by the turbine. So let us shift this W here and this value here. So W is equal to 2993 minus 226 minus 50. So this is the value. You can calculate and tell me this. This is a simple calculation. 2990 minus 226 can give you something like 2767 minus 50, 2717. So W is equal to 2717 kilojoule per kg. Since the answer is asked in kilojoule per kg of steam. Okay, so this is in kilojoule per kg. Correct, Nagasai. That's what we got here. 2717 kilojoule per kg. Yeah, there is no use in this case, in this particular, but generally there's one lesson called properties of pure substances, which I thought, I'll be discussing later after discussing entropy and all. This situation is called superheated steam actually. Okay, there you'll be having U and H values tables, which you call generally steam tables that you'll be looking at. Yeah, that's what the important point. So you won't get confused if you write these constitutive equations. You'll know what quantities to take from the given data. Okay, data will give a lot of things to confuse you, but generally which points of data should be selected, that depends entirely on your constitutive equations. Okay, so we'll go for the next question now. The internal energy of an ideal gas is a function of, just now I told you, since they mentioned this ideal gas, we'll go for temperature only. Otherwise, it's volume and temperature for internal gas. Okay. Internal energy combination for finding internal energy of a gas in general for any gas. Okay, but since it is ideal gas, as I told you in one of the questions ahead, we see only temperature. Okay, that's why we see change in internal energy is dependent on only on change in temperature as well for ideal gases. D, correct, Nagasai. Answer is temperature only. What about remaining people? See, 9 people are around watching this. Then some of you are not responding. Chinao, okay. So see here. Okay, see here the exit enthalpy nozzle. I hope this is some similar kind of question. So please work out this question and tell me the answer. Correct, Vamsi? D is the correct answer. So please work out this question. It's a simple question. Steam initial enthalpy is given. Then they are asking for the exit enthalpy. Both inlet and exit velocities are given. It's already 11:22. So please, 85 is the answer, Deepak. Okay, let me check. Could be a chance because steam enthalpy will drop. So initially if it's 100, now it should be less than 100. So 85 is reasonably logically correct. So let us write this solution. So steam at an initial enthalpy of 100 kilojoule per kg and at inlet velocity of 100 meters per second enters an insulated horizontal nozzle. See, in this word insulated horizontal nozzle, he mentioned 2 data points. What are they? Look, suppose if this is your nozzle, where this is your control volume, boundary by open system. See, insulated horizontal means the potential differences is 0, means that potential head differences is 0, and also the nozzle is insulated. No heat interactions basically. Okay, so if you apply steady flow energy equation, Q minus W is equal to delta KE plus delta PE plus delta H. This question was asked in GATE 2016 for 2 marks. Okay, so Q minus W is equal to delta KE and all. So Q is 0 because of this word insulated. Potential energy change is also 0 because of the word horizontal. And you know, nozzles generally they are not capable of producing any work. So delta KE plus delta H is equal to 0. So if this is the case, if you write in specific terms, V out square minus V in square divided by 2 is equal to H in minus H out. So now he's asking for H outlet with all the other values given. H in minus V out square minus V in square divided by 2. So now we have all these 3 data points. H inlet is given, inlet velocity is given, exit velocity is given. You can perform this calculation. So H outlet is equal to H inlet 100 kilojoules per kg, but we need to perform this in joules per kg because velocities will put in meters per second, minus V outlet 200 minus 100 square. So 200 square minus 100 square is 300 into 100 divided by 2. Now since he is asking in kilojoules, we can cancel 110 cube. So 30 by 2 is 15, 100 minus 15 is 85 kilojoules per kg because we are not multiplying mass anywhere. Okay? So H out is 85 kilojoule per kg. Chinav, that's the fault. See, for enthalpy of steam, how can you get 500 kilojoule per kg of enthalpy at inlet? How can you get 85,000 as outlet? Please look at calculations carefully, Chinav. Nothing, everything is fine. Okay. So we'll go for next question. If you have any doubts, you can ask regarding this question. Okay, so can I go for the next question? Okay, so this is the question. A calorifically perfect gas, specific heat at constant pressure, 1000 joule per kg Kelvin, enters and leaves a gas turbine with same velocity. Means there is nothing changing kinetic energy macroscopically. The temperature of the gas at the turbine entry and exit are 1100 and 400 respectively. The power produced is 4.6 megawatts and heat escapes at 300 kilojoules per second. So heat escape rate is very huge here, 300 watts. See here through the turbine casing. The mass flow rate of the gas means generally you know turbines they generally deal with kgs of steam per second. So let us try to solve this question. First of all, I'll give you time. This is a GATE 2017 question for 2 marks. So please try to solve this question. Later I'll solve for you. Take some time and solve this. Please try to solve this question. A calorically perfect gas, specific heat at constant pressure 1000 joule per kg Kelvin. So let me write data for you. Cp is given 1000 joule per kg Kelvin. Okay. Next, enters and leaves a gas turbine with same velocity. So V inlet is same as V exit. Okay. The temperature of the gas at NT, so T in is equal to 1100 Kelvin. T exit is equal to 400 Kelvin. Okay. Power produced is 4.6 megawatts. So W dot is 4.6 megawatts. If you write things in kilowatts, this is 4600 kilowatts. Okay. Heat lost from the turbine casing. Heat escapes at a rate of 300 kilojoules per second. So heat lost is equal to minus 300 kilowatts. I am putting a minus sign because in the steady flow energy equation we assumed that this Q dot is added to the system, but here it's rejected, so we are putting minus 300. Okay, from the turbine casing, mass flow rate of the gas. So m dot is equal to dash, and we want this value in kg per second. Yes. So this is a turbine generally, in which steam expands, inlet, outlet, so control volume. Let me draw this control volume a bit properly. Okay, so there is some heat loss and some work output by this turbine. Option B, Deepak, 7 kg per second. Okay, since options are closed, let me work out the things. So see here, Q dot minus W dot is equal to delta KE dot plus delta PE dot plus delta H dot. So this implies Q dot is minus 300 kilowatts. So this kilowatts I am writing 10 cube minus 4.6 megawatts is given. So this, if I write it in kilowatts, 4600 into 10 cube, this is in watts, is equal to m dot into, see, potential energy changes we are neglecting because no data is given regarding potential energy changes. So enthalpy changes are also given, Cp and these temperatures are given, so we can work out. So V exit minus V out square minus V in square divided by 2. But anyhow, this term is 0 because V inlet is same as V outlet, because it's given in the question clearly. Steam is entering and leaving at same velocities. Okay, so plus potential changes we already neglected, plus delta H, m dot into Cp into T out minus T in. Now for what value this fellow is asking for, this m dot. Okay, let us write this. So minus, if you take minus 10 cube also common, you have 300 plus 4600 is equal to m dot into Cp. Since we are substituting everything in watts, let us write Cp also. What's the value of Cp given? 1000 joule per kg Kelvin. Okay, so this is 10 cube into T out. What is T out? That is given 400 and T in is 1100. So the difference is 700. Of course, this is minus because 400 minus 1100. So these are the values that are available to us. So plus and plus, because both the minus signs gets cancelled on both sides of the equation. 10 cube gets cancelled. So this implies 4900 is equal to m dot into 700. So if you see, this 2 zeros and 2 zeros gets cancelled. 7 cancel this 49 7 times. So m dot is equal to 7.00 kg per second. Is the mass flow rate. Correct. 7 is the correct answer. I think no use of calculator for this. Correct. So 7 is the correct answer. Yeah, Chinao, correct. So we'll go for next question quickly. I hope still 2 questions are left with us. Okay. Steam flows through a nozzle at a mass flow rate of m dot is equal to 0.1 kg per second. Okay. Mass flow is given Mass flow rate is given 0.1 kg per second with a heat loss of 5 kilowatts. So 5 kilowatts heat is also going out of the system. Fine. The enthalpies at inlet and exit are 2500 and 2350 kilojoule per kg. Okay. Assuming negligible velocity at inlet, so C1 is 0. The steam exit velocity is dash. Cut to 2 decimal places. This is GATE 2018 question. So let us try to work out the things. Solution. See, 5 kilowatts is already given here, so you can't put Q dot as 0 this time. Of course, even though 5 kilowatts is very small when compared to the huge values like 2500 and 2350 and all these things, but still we'll consider Q dot. So Q dot minus W dot is equal to delta K dot plus delta P dot plus delta H dot. Okay. So now this W dot is 0 anyhow because nozzle doesn't produce any work output. And if you see, potential data is not mentioned here. So data related to the potential energies is not mentioned here. So delta PA is also 0. So Q dot minus 5 kilowatts. So minus 5 because heat is being lost from the system. So minus 5 kilowatts. So for this kilowatts, let us put 10 cube is equal to M dot. Mass flow rate is given as 0.1. So 0.1 into V out square divided by 2 because V inlet is given 0. It's given already C1 is 0 plus delta H. M dot again 0.1 because mass flow rate is same throughout into H2 minus H1 means H out minus H initial. So 2350 minus 2500 will give you minus 150. So if you see the values, now this 0.1 cancels this 0. So total it is minus 15 and this is minus 5000. So if you perform this calculation, this is minus 5000. And I guess this is in kilojoules. So we have one more 10 cube here because we need to convert into joules actually. So minus 5000. So if this is minus 15,000, if this minus 15,000 goes to the other side, this will be plus 15,000 is equal to 0.1. Let me write this equation in a new page so you will feel the things clearly. Okay, 14.1. I think the value could be a bit more, Deepak, because generally nozzles they accelerate the fluid in hundreds of meters per second. So let us see. Minus 447 could be reasonably correct, Vamsi. Let us see what could be the value. So let us see here. Okay. This implies minus 5000 is equal to 0.1 into V out square by 2 minus 15,000. This is what we have. So if you bring this 15,000 this side, we have 10,000. Yeah, 10,000 is equal to 0.1 into V out square divided by 2. Till this moment, I didn't perform any calculations. Please see here. V out square is equal to this 10. If it comes here, this is 10 power 5 into 2. So basically 20 into 10 power 4. This is what we have in meter square per second square. So V out is equal to square root of 20 into 100 because square root of 10 power 4 is 10 square. 100 meters per second. So if you know the value of square root of 20, you can write the things. Let us simplify this. V out is equal to this root 20 can be written as 4 into 5. So 200 into square root of 5 meters per second. And root 5 is 2.23. So generally 444, yeah, 447 something would be correct. So 447.21, all of you. 447.21 meters per second. Okay. See, that's why in exam when you get values, you need to check. You need to look at the physics that's governing the problem. Okay. So see, when he told velocity is around 14 meters per second or something, I told, yeah, because generally nozzles, they accelerate the fluid in that range, 300 to 400. Okay. Maybe more than that if they go for supersonic levels and all. So generally, you should get some value in order of 447.21. This could be reasonably correct. Okay. So one last question of the day. After solving this, we'll end up the session. just 10 minutes. For this, actually I thought of performing the analysis, but since we don't have any time and all, even I have some other work. So please see here. Generally, if there is an insulated vessel with some gas at temperatures Ti, Pi, and all these things, and in this pipeline, if because of this wall, this is an automated pressure controlled wall. If once the pressure in both these chambers, means in the pipeline and this chamber, is same, actually this belongs to unsteady flow, on which we don't have any gate questions as of now. But see here, this is unsteady flow because of this pressure difference, some mass starts coming in, and if you treat this as the system, there is some mass flow into the system, but there is no mass exit, which means some mass is getting stored inside the system. Okay, generally you take this for filling gas cylinders and all these things, because there is a pipeline which carries the fluid inside it, and you will be taking stock of some fluid in a container like our gas cylinders and all these things. Okay, so Ti, Pi, and let us suppose this is Pa and Ta in general. So once after some gas starts coming in, final temperature is gamma times. Final temperature will be gamma times of this pipeline temperatures. This is the relation. Okay, so generally because of this pressure difference, initially when this Pa is more and this Pa is less, because of the pressure difference, some mass or some gas starts flowing, because fluids flow from high energy to low energy, so gas starts coming in. But once the pressure is same on both sides, it balances the throttle valve, so the valve doesn't open anything beyond that, so gas stops flowing. So the moment gas starts coming in to the moment the gas gets filled, this is an unsteady control mass system or unsteady open system, because you see some gas, there is some mass inlet but there is no mass outlet. Similarly, there is some energy inlet but there is no energy outlet. So in this case, this final temperature of this vessel Tf will be Cp by Cv times of this pipeline temperature. So if you see, it's given 400 Kelvin here. So since we are taking this as A, so A is given, so we have gamma is equal to 1.4 and Ta is equal to 400 Kelvin. Tf is equal to final temperature of A in the tank, which we are talking is gamma times Ta, so which is 1.4 into 400, which is 560 Kelvin. Okay, actually this is unsteady control mass systems, but control volume systems, unsteady control volume systems. But right now I'm not dealing with derivations of all these things. So, but it's enough for you to know this, that the final temperature in this box will be gamma times of this pipeline temperature. Okay, so please make a note of this thing for this last question, and I hope we finished the questions. Yeah, these are the solutions for answer key basically for the 18 questions that we discussed in today's class. So if you see, this is how things work in analysis of open systems. So this is the last thermodynamics class that is being taken by me. For entropy and all, another faculty is going to take you. Okay, so we'll end up this session here. So I hope I'm clear with you with the basics like zeroth law of thermodynamics, first law of thermodynamics for open and closed systems, and we have done some enough analysis on the things. Okay, so yeah, I hope we covered all previous gate questions till 2018, maybe beyond that at some points. Okay, so if you all are okay with this, we'll wind up this session now. Okay, so is there any issues here so far? If everything is fine, then we'll wind up the session. Anyhow, I gave you my contact, so if you have any issues at any moment, you can mail to me. I'll be responding. I'll be very happy to respond to your questions. Okay, at all times. Okay, so take care. I'll be sharing the notes of these two chapters as well, so you can get access with the things. Okay, so thank you all. We'll be winding up the session.